Okay, so today we're going to talk about amortized analysis. This is basically a different way of looking at the runtime of an algorithm. And our idea here is that suppose I have some data structure or some algorithm and I'm doing many different operations. Now I can look at the runtime of one operation and just ask what is the worst case runtime of this one operation. And then if I have n operations, I can multiply that worst case runtime by n and say this is the worst case runtime for n operations. But there are many cases in which if I do a sequence of n operations, I actually get a better overall runtime than the worst case runtime of one operation times n. So this is what we want to focus on in amortized analysis. And let me just give you a very simple example. So the example is the example of a counter. So imagine that I have a counter, and let's say this is a binary counter, and let's say I have k digits. So counter with k digits. And this is basically an array of bits, an array of zeros and ones. And there are k digits in it. And initially, everything is 0. Okay. And you can imagine that these k digits are this number. This doesn't fit in a normal integer or anything. I have to really keep it as an array of bits. And let's say that I have only one operation, and my one operation is to increase the number in the counter by 1. So the only operation I have is increment. Okay. And imagine that I do this operation n times. Okay. So I know that I'm doing the increment operation n times. So at the end of it, of course, my array will contain the binary representation of the number n, because after one increment, it will become 1, then it becomes 2, and so on. Now, if I want to analyze the runtime here, I can say that, well, I have k digits. So the worst case runtime of one increment operation is OK, right? Because when I'm doing one increment, in the worst case, I have to change all of my digits. So I can say the worst case runtime for one operation is OK. And so if I have n operations, my overall runtime is OK times n. Okay. This is correct, but it's not really tight. So here's the thing. Instead of OKN, let's just imagine all of our operations together. So I have all of these bits, and I'm constantly adding 1 to this number. How often does the last bit change? The last bit changes every time. So the last bit is just telling me if the number is odd or even. So if I look at this last bit, every time that I'm increasing this number, this last bit is changing. But how often does the second last bit change? It only changes half of the time, right? And then the next bit changes only 1/4 of the time, and so on. So if I look at the total number of changes, which is also, of course, my runtime, total number of bit changes, it's going to be at most n changes in this bit, plus n/2 changes in this one, plus n/4 changes in the next one, and so on. And the last bit is going to change at most n/2 to the power of k minus 1. Okay. Of course, this is a geometric series, and I mean, it's ending at k minus 1, but I can just imagine that it goes on forever, and then I can say that this is at most 2 times n. Okay. And of course, 2 times n is in O of n. So this means that when I'm doing n increments, my total runtime is actually completely independent of k. It's just On. Right? Now, this was just doing a total runtime analysis, but in cases like this, I would say that the amortized runtime of one increment operation is O1. So basically, when I'm talking about the amortized runtime, I'm saying imagine that I have a sequence of operations instead of just one operation. And imagine that I have the worst possible sequence of operations. What is the average runtime for each operation in this sequence? Okay. So this is what I'm doing when I'm doing amortized runtime. I say consider any sequence and take the worst possible sequence of length n. Okay. So let O1, O2 to On be the worst possible sequence of length n of operations, which means that I'm doing exactly n operations, but I'm choosing the combination of n operations that give me the worst total time. Okay, be the worst case, the worst sequence of n operations. Then we say that the amortized cost or the amortized time of one operation is just the total time that I'm spending on this sequence divided by n. Okay. Amortized cost of one operation is simply the total time I'm spending on operation 1, operation 2, so on to operation n divided by n. Now, a very important thing here is that we're not doing average case analysis. We're still doing worst case analysis. So I'm looking at all the possible sequences of operations of length n, and I'm taking the worst sequence. And then in that sequence, I'm saying, okay, the average cost of one operation was this much. So that's how I'm defining my amortized runtime. Now, with this kind of definition, I can say that incrementing a counter, no matter how many bits it has an amortized cost of O1, right? So one increment has, well, a worst case runtime, which is okay. And then it has an amortized runtime, which we established is O1. Okay. Now, of course, we would care more about amortized runtimes when we're doing a lot of operations. And we will see many examples of that. Okay, so let's say I have this counter and so on. So this is how I define my amortized runtime. But there is also another way of defining amortized runtime, which is also interesting. Sometimes they call it the accounting method or the potential method, or some people actually distinguish between the two. Basically, the idea is that every time I do an operation, I can also store some value somewhere in my data structure. So imagine that I have to pay $1 for every unit of time in my execution. Okay. And sometimes I just pay $1 extra for no reason, and I just store it somewhere in my data structure to use it later, right? If I want the total cost of a sequence of operations, this would only over approximate the total cost. Okay, so let me just give you this example of a counter again. So here's what I'm going to do. I'm going to say I have my counter, and initially everything is 0. Okay. Now I do an increment. When I do an increment, some of my zeros become 1. I basically have to start at the end of my array, and I have to see what changes I have to make. In this case, I have to turn this one into a 1, and I just stop. I don't change the rest of them. So this one took just one operation. So the cost here, the real cost, was just 1. But additionally, I say that whenever I turn a 0 to a 1, I'm going to put $1 of money on that 1. Okay, so I created the 1, and I'm also putting $1 here. Okay, so now with this new rule that I have in my mind, the cost of this increment was actually 2, because I changed I did one operation here, changing the 0 to the 1, and I also put $1 on top of the 1. Okay. Now, next time that I do increment, again, here's what's going to happen. I have this 1 here, and I have to change it to a 0. Okay, so that's going to cost me. But I already have $1 on top of this 1, so I'm just going to use that dollar to pay for it. So I changed this 1 to 0, and I paid for it by the dollar that I had already there. Now I have to change this 0 to a 1. I change it to a 1, I have to pay for it. And then I also put a dollar here, so I have to pay for that dollar too. So again, the cost of my increment was 2. Okay, and then I have zeros here. Let's do this one more time. I do increment again. Okay, this is 0, and I'm just changing it to a 1, right? So I changed this 0 to a 1, and I said whenever I create a 1, I put a dollar on top of it, and then I don't have to change anything else. So again, the cost of my increment was 2. Let me do one more. I'm getting really tired of this, but I have to really show it to you. So here's the thing. I do another increment. I have a 1 here. I have to change it to 0. I have to pay a cost of 1 to do that, but I already have a dollar saved on there. So I just pay that cost using that dollar, turn it into a 0. I take the next one. I also turn it to a 0 using that dollar. And then I get to this 0. I have to turn it to a 1. That's a cost of 1. And I have to put a dollar on top of it. That's a cost of 2. So no matter what I do, my increment is always going to cost me 2 units. So the cost of each increment is all 1. It's basically 2. Okay. Now, how do we actually mathematically formalize this idea? Well, the idea is actually very simple. Every operation has a real cost, a real runtime. And I can also assign to it what I call an amortized cost. Okay. So here's what I'm going to do. For every operation, let's call this operation OI. Okay, which has, let's say, some real cost or real runtime CI. I assign an imaginary runtime or an amortized runtime. Let's call this one C hat I. I assign C hat I. And this C hat I is basically the amortized runtime that I'm assigning to operation I. Now, what is the rule that I have to satisfy? I want to say that over any sequence of operations, I'm always over approximating my total cost. I'm never under approximating it. So I want to say that this is the property. I want to say for every sequence of operations, let's call it O1, O2 to ON. If I look at the real cost of these operations, so if I take the sum of CI, this should be less than or equal to the amortized cost that I gave them. Okay. As long as I have this, it doesn't matter if the amortized cost for one operation is smaller than its actual cost. Because what I'm proving here is that for any sequence of operations, I'm over approximating the total cost of those operations. Okay. And this is exactly what I'm doing with these dollars here. Basically, whenever I'm putting a dollar there, I'm saying I'm intentionally increasing my C bar I. I'm intentionally increasing the amortized cost that I'm assigning to the current operation. Now, why do I do this? Because later on, I want to use that dollar to decrease the cost that I'm assigning to some other operation. Okay. So again, using this dollar method, you can see that every increment here cost me 2 units, which is basically O1. So every increment is an O1 amortized time. Now, these are 2 different definitions of amortized runtime, but they're very close. Actually, this second one is a bit more general. Okay. Now, let me give you some more examples of this. So the first example that comes to my mind is a stack. So a stack is basically an array, and you can only add to the end of it and remove from the end of it. So you have push and pop. And let's say you also have a maximum size, so you're never going to exceed the size of your array, okay? Or maybe you've implemented it with some other data structure. You can also implement it with a linked list. So I have two operations. I have push and I have pop. And when I push, I give it some value to push. So imagine if I have this stack implemented as some sort of a linked list. I just have a linked list of values. Let's say it's a doubly linked list. So every element has a pointer to the next element and the previous element. And I can do push and pop. And of course, all I need to do here is to have a pointer to the last element, right? So whenever I push, I'm just adding a new element to the end and changing a constant number of pointers. It's very easy. When I'm popping, I'm also changing a constant number of elements. That's also easy. So the worst case runtime of both push and pop is all 1. But now let's say that I change my pop so that it takes a parameter k and it actually removes the last k items. Okay. So now the worst case runtime of pop is actually on, because it's possible that I've pushed n items in there and then I'm just doing 1 pop to pop everything, right? But again, if we look at this in the amortized way, the idea is that, well, I can never pop more than what I have pushed, right? So if I use the first idea of amortization, the idea of just looking at the total cost, every item is added at most once and removed at most once. So my total cost should be on. So the amortized cost over n operations should just be O1 for both push and pop. But I can also, again, do it using this dollar method or potential method. So again, here what I do is that I say whenever you just put $1 on top of it. Okay. So I'm going to start, of course, with an empty set, with an empty stack. And every time that I pushed something, I put $1 on it. Okay. Now, what is the cost to push another item? Well, I have some constant amount of work. Let's say, I don't know, I have to change 5 pointers to add this new item. And then I'm also putting $1 on top of it. So, or instead of $1, let's say I'm putting $10 on top of it. Constants don't matter here, right? So I'm putting $10 on top of it. It's going to cost me 15 units to push something. So the cost for pushing is O1. Now, when I use pop k, when I want to pop k elements, basically, I just use the dollars stored on top of every element to pay for all of my pop operations. Okay. So effectively, I get my pop operations for free. You can say that both push and pop have amortized runtimes of O1, but I can also even say that my pop has an amortized runtime of 0. Right? If I say my push has an amortized runtime of 15, and if the amount of money that I'm saving there is enough to pay for all of my pops, then I can say my pops just have an amortized runtime of 0. You can also assign a negative amortized cost if you want to. But not a big deal, don't do that. So yeah, in practice, we don't really want to make it better than O1. So we're happy with O1. Basically, it doesn't matter that I can pop k elements. If I'm doing amortized runtime analysis, I can say that every push takes O1 amortized time and every pop also takes O1 amortized time. Okay. Let me show you a better example of this. And a better example is actually how a vector works in C++. Or this is basically a resizable array. Okay. So suppose that, well, I don't know if any of you have ever done any C programming before the standard template library and so on. So in the days of C, we actually had arrays. We had memory management. We could allocate some amount of memory, but we couldn't have things like vectors that change size, right? So actually, the way a vector works is using arrays. let me actually show you this. Let me just implement my own vector. Okay. So here's the idea. Let's say I want to create a new structure that is basically a vector of integers. I just call it vector. And I'm not going to use a template here because that's too much C++. So my vector can only contain an array inside. So I have to dynamically decide when I actually allocate and deallocate. And let's say that I have only one operation here. And let's say that that one operation is pushback, which just adds one element to the end of my vector. Okay. So here's what I'm going to do. I'm going to say I have a size here, which is basically the number of elements in my vector. And I'm also going to have a capacity, which is the number of elements that I can possibly put into my vector. And then I'm going to also have a pointer to an array, or let's call it A. And this is basically pointing to the first element in this vector. Okay, so A plus 1 would point to the second element and so on. Now, initially, I would just say something like this. I would say that initially my size is 0, my capacity is 1, and let's say my A is just an array of size 1. So basically, my capacity is always the size of my array. Okay. Now, I have just one operation, and this one operation is pushback, which adds one element to the end of my array. So it takes X, and it adds it to the end. Now, here's the thing. If my size is less than my capacity, I can already put this element into my array, and I don't have a problem, right? So if the size is less than capacity, I just say A size becomes X, and then I have to increase the size. So I do this again. Okay. My size increases by 1, and X is basically added in. The interesting case is when the size is equal to the capacity. So my array is full, and now at this point, suddenly I see that I have to insert some new number. So what can I do here? Well, I can just allocate a new array somewhere else in memory and copy everything. Now, a stupid way to do this is to create an array of capacity plus 1. But I'm going to just double my capacity instead. So I'm going to say otherwise. Here's what I'm doing. I'm going to double my capacity. What does this mean? Well, I'm just going to have another array, let's call it B, and it's going to be of size capacity times 2. Okay, and now I'm going to copy everything that I had in A into B. So for every I from 0, to size, I just say BI becomes AI. Okay. Now I copied everything. Now I say my capacity is doubled, and I say maybe delete whatever you had in A, get rid of A, and A becomes B. So now I'm pointing to the new array. And finally here, I'm doing the pushback. So I just add the elements. Okay. That's it. That's my implementation of a vector. And actually, this is very similar to how the real vector in C++ works. Now, if you look at my pushback operation, what is the worst case runtime of my pushback operation? Of course, the best case is here when I have to do only a constant amount of work. But the worst case is here when I have to basically create a whole new array, which is twice the size of my previous array, and I have to copy everything. So if I have n elements or n operations, the worst case runtime of a pushback is O(n). So based on this, you might say that, well, if I do n operations, there are n pushbacks, each of them is taking O(n), the total runtime is O(n) squared. Again, this is true, but it's not a good bound. The point here is that every time that I'm doing one of these expensive operations, my capacity is doubling, right? So how many times am I going to do this? At most log n, right? So if I have n pushback operations, I know that at most log n of them are expensive operations, and the rest of them are these cheap operations where they're just being done in O1. So this is already telling me my total runtime is O n log n, right? But I can do even better than that. What is the total runtime of these expensive operations? So here's the thing. When I have my expensive operations, what's happening to my capacity? Basically, my capacity is going from 1 to 2 to 4 to 8 to 16 and so on. Okay. Now, every time the cost that I'm paying is some constant times my current capacity, right? I'm basically just creating an array which is of size capacity times 2, and then I'm doing this copying, which is just taking O of capacity and so on. So basically, here I'm paying some cost C to go from size 1 to size 2. And then to go from size 2 to size 4, I'm paying at most 2 times C. And then here I'm paying 4 times C, and so on. Okay? And C is just a constant, whatever it is. I don't know exactly what it is. Okay. Now, if I sum up all of these, and this, of course, goes on until this multiplier gets larger than n. Right? So again, I just have the sum of powers of 2. So what I have is this. It's the sum of 2 to the power of I times C, where 2 to the power of I is less than or equal to n. Okay? But this is at most C times 2 times n, which is in O of n. Okay? So the total runtime of n operations, n pushback operations, is O(n). So that means that the amortized runtime of one pushback operation is only O1. And that's why in all of your codes, you just use vector and you assume that all of the operations take O1 because they take amortized O1. Of course, I could also do it using this dollar method, put some everything that you insert and then use it to double the size. But you get the idea. You can do it in both ways. Now let's solve some real problems. Okay, let me see which one do I like first. Yeah, let me do the DSU thing. So remember when we were talking about disjoint sets with union, I told you that if you do path compression, then the overall runtime would be n log star n. I want to prove that to you now. And basically, I want to show that every operation will take an amortized runtime of O log star n. Okay, so remember, we have disjoint sets with union. Now, in the lecture, when I was talking about this, I said that we have two operations. We had a merge operation, and we had a query operation, which asked whether two different elements are in the same set or not. But I'm going to change my operations a little bit because this makes it easier to talk about their amortized runtime. So I'm going to say we have a find root operation, which basically takes some vertex u and tells me what is the root of the tree that contains u. Okay. And then let's say I have a link operation that takes two roots, R1 and R2, and makes one of them a child of the other. Okay. Now, this is not very different because, well, remember when we wanted to check if two different items are in the same set, we just did find root for both of them. And then we just checked, do they have the same root? And of course, linking is also just like merging. So when I want to do merge, I first find the root of both of them, and then I link those two roots. So, and of course, I'm doing this disjoint set with union with trees. And I'm assuming that I'm also doing path compression. Okay, so just as some sort of a reminder, let's say that I'm doing find root on this vertex u. So the way this worked is that I started at u and kept going up until I reached to some root. Okay, and then I would also do path compression, which means that I would connect everything that I saw in this path directly to the root. This one was already connected. I would also connect these ones to the root. Okay. Now, I gave you some intuition when I was talking about DSU, and the intuition was that this makes all of the paths to the root kind of shorter. So next time, if I want to query U, if I want to find the root of U, I'll find it immediately, right? But it also makes the path from this vertex shorter because now this one is also directly connected to the root. And if this one had some other children, then that path is also now shorter. So a lot of the paths get shorter by just doing path compression. So path compression is a good idea. And we got it pretty much for free because this was a path that I had to go through anyway. So my runtime is just getting multiplied by a constant when I'm making all of these new links that are connecting everything here directly to the root. Okay. Now, let's look at our worst case runtime. Well, my worst case runtime for find root, if you remember this, was O log n, because we had this idea that we always merge the smaller tree into the larger tree. So every time that we were merging two trees together, every time that the root of some vertex was changing, let's say, the size of the tree containing that vertex doubled. So the total depth of any of my trees could be at most O log n. So find root takes O log n worst case. Now, how much time does link take in the worst case? Well, because I'm saying that link already knows the two roots, that's just O1. Okay. So if I look at my worst case execution time, find root is going to take O log n, and link is going to take O1. Okay. But now I want to also talk about the amortized runtime. And of course, I'm going to assign an amortized runtime of O1 to link because it's already O1. I'm happy with that. But I want to say that the amortized runtime of find root is just O log star n. So this is the thing that is interesting to me to prove this. Okay. Now, again, I'm going to just make some small changes. I'm going to change the link because I need some notion of rank that I'm going to use in my analysis. So here's the small change. I'm going to say every vertex has a rank. Okay, every vertex U has a rank RU. And initially, all of the ranks are 0. Okay. Now, when I want to link two different vertices, oh, I'm using R for root, sorry. So let's just call it rank of U. And initially, they're all 0. Now, I want to just have the same rule as before that I always merge the smaller tree into the larger tree, but I'm going to use these ranks to do that. So here are the rules. When I want to do this link, when I want to link R1 and R2, I simply check their ranks. If one of them has a smaller rank, the one that has a smaller rank becomes the child of the one that has a larger rank. So I say if the rank of R1 is less than the rank of R2, then R1's parent becomes R2. And similarly, I say if the rank of R2 is less than the rank of R1, then R2 becomes the child and R2's parent becomes R1. The only interesting case is when they have the same rank. And when they have the same rank, I just don't care. I make one of them the root and I increase the rank of the root. Okay? So otherwise, if the ranks are already the same, rank of R1 is equal to the rank of R2, let's say, then all I do is that I again say, let's say R1 is the child, so R1's parent becomes R2, but I also increase the rank of R2. Okay. Now, why am I using ranks and so on? Why am I not just using subtree size or height? It doesn't really matter because the same argument goes through, right? So you can easily prove that if I have an element with a rank of k, then its subtree has at least 2 to the power of k elements in it, right? Sorry, if I have a root of rank k. Of course, I don't care about the rank of things that are not roots because I'm not going to use those. Okay, and that's pretty easy to prove because the only way that I can get a rank of k is if I have two different roots, R1 and R2, each with rank of k minus 1, and I link them together. And then each of them already had 2 to the power of k minus 1 nodes. So when I put 2 times 2 to the power of k minus 1, I get 2 to the power of k. Okay, so this is how my link is going to work. And again, my link has amortized runtime 01 and worst case runtime also 01. I want to focus on the find roots. So imagine that I'm doing n different find root operations. But of course, I don't know in what order, right? So, and I have to consider the worst case possible scenario. So imagine n times find root. Okay. I want to prove some lemmas, and I want to prove these lemmas about the ranks. So here's the first thing I want to ask you. At any given time, how many elements can I have of a particular rank? So how many elements of rank R, or I used R for root again. Okay, of rank K can I have at any given time? I just want a bound. I don't want an exact number. Okay. So here's the thing. If I have an element, if I have some vertex that has rank K, what does it mean? It means that its subtree contains at least 2 to the power of k different vertices, right? So here I have at least 2 to the power of k vertices. Okay. And additionally, the subtree of a rank k vertex does not contain any other rank k vertices, right? Because of course, the way I got to rank k was by merging rank k minus 1, and I got that by k minus 2 and so on. If I had a rank k vertex anywhere in this subtree, then the rank of the root would be k plus 1 or higher. Okay, so this means that the subtrees of all the vertices that have a rank of k are disjoint from each other, right? And each one of them has at least 2 to the power of k vertices, and I have n vertices overall. So I can have at most n over 2 to the power of k elements of rank k at any time. Okay? Because for each one of them, again, I have a subtree of size 2 to the power of k, and all of these are separate, and I have n vertices. Okay, but let me ask you something else. Instead of asking how many elements of rank k can I have at the same time, let's suppose that I ask you how many of the elements, how many of my vertices can possibly have rank k at some time during the execution of my algorithm. Okay. So how many elements can have rank k at some point? So I'm looking at each one of my elements. I'm looking at its rank at every point of time. And if at any point it has rank k, I count it in. Okay. Now, here's the thing. A very simple observation. The ranks of my elements only ever go up. They never go down. So if I have an element that had rank k at some point, by the end of my algorithm, it should either have rank k or k plus 1 or k plus 2, so on. Okay. But at the end of my algorithm, I know that there are at most these many vertices that have rank k. So n over 2 to the power of k. And then how many vertices can have rank k plus 1? Well, n over 2 to the power of k plus 1. How many vertices can have rank k plus 2? N over 2 to the power of k plus 2, and so on. Okay, so this is going to give me a bound on the number of vertices that had rank k at some point during my execution, because these are exactly the vertices that have a rank of bigger than k, bigger than or equal to k at the end of my execution. Okay, but again, this sum appears over and over again. Every term is half of the previous term. So this is at most 2n over 2 to the power of k, or n over 2 to the power of k minus 1. Okay, so just remember these lemmas. We're going to use these lemmas in our analysis of this algorithm. Okay, now what? So let me just give you a refresher on what log star was before we continue with this. So I defined log star of n like this. I said that log star of n is, did I say 0 or 1? So let's say 0 if n is less than or equal to 1. And it's 1 plus log star of log of n if n is greater than 1. Okay. So this is the function that we would like to have in our final runtime. Now, just to go over this, this means that log star of 1 is 0. Log star of 2 is 1, right? Because that's 1 plus log star of 1. And then log star of 2 to the power of 2 is 2. Log star of 2 to the power of 2 to the power of 2 is 3, and so on. So generally, if I have a tower of exponentials, and there are like k different 2's in this tower of exponentials, and I take the log star of this whole number, that would be k. Okay. Just to give you a sense of how crazy this function is and like how slow it grows, let me use Python for the first time in my life. So here's the thing. 2 is, of course, 2. 2 to the power of 2 is 4. Has a log star of 2. If I want a log star of 3, I have to add another one. So 16 has a log star of 3. So if I take 2 to the power of 16, this number has a log star of 4. Now, what should I do to get a log star of 5? It's this suddenly. Okay, it's very long. This will never happen in practice. So in practice, whatever n you're working with is going to have a log star of at most 5. Okay, so that means that if I prove to you that the amortized runtime of my operation is O log star n, for all practical purposes, the amortized runtime is like 5. Okay, but again, very importantly, theoretically, this is not the same as O1, because the limit of log star n as n tends to infinity is infinity. Okay, it's just that it grows very slowly. And for all practical purposes, we're always working with numbers that are smaller than whatever this number is. So log star is small. Okay. Let me continue with the analysis. Let me look at my notes. Okay. So here's what I'm going to do. First of all, again, as we said here, link takes constant time. I don't care about that. I want to only consider find root operations. Right, so let's say I'm doing my find root operation. What does that operation look like? Where I'm basically starting at some vertex u, and I keep going to its parent, and so on until I get to the root. Right, and of course, after that, I also do path compression. But that's only going to take the same amount of time as traversing the whole path. So the path compression part is just multiplying my time by a constant, so I can just ignore the path compression time when I'm doing my analysis. So I just want to know how many times do I go from a vertex u to its parent. if I can know that, I have my amortized runtime within a constant factor. So here's the magic number that I care about. It's the total number of times that I go from one vertex U to its parent. Okay, that I go from any vertex U to its parent, U dot parent. And this is, of course, over n operations, and these operations can be any combination of find, root, and link. Okay. Now, I'm going to divide all of my different vertices based on the log star of their rank. So I'm going to create different groups of vertices. I will have one group for the vertices that have a log star of rank of 0. And then the vertices whose log star of rank is 1. The vertices whose log star of rank is 2, and so on. Okay, so how does this look like? Basically, I have one group. Let's say this is my group. This is the rank of the vertices in this group. Let's say I have one group for rank 0, because for 0 log star is not defined, whatever. And I have one group for vertices of rank 1. I have one group for vertices of rank 2 and 3. Then I have one group for vertices of rank from 4 to 15, right? And actually, let me just look at these as segments like this. And then I will have another group for vertices of rank 16 to whatever that one was, 2 to the power of 16 minus 1, this thing. And generally, if you look at my groups, all of my groups are of this form. They are vertices of form that have a rank from 2 to the power of I, or actually, let me say it like this, that have a rank from I itself is also a power of 2, but I don't care, to 2 to the power of I minus 1. Right? I don't have this for all i's. I'm just saying that for every group, there is an I such that this group corresponds to vertices that have a rank between I to 2 to the power of I minus 1. Okay? Now, so these are my groups. Again, what I wanted to find is the total number of times that I go from some vertex U to its parent. Now, I want to just break this down into several different cases. Okay? So when I go from a vertex to its parent, maybe the parent is already the root. Okay? So I'm going to call this case 1 or C1. This is the case where U dot parent is root. Okay. Plus, the second case I want to consider is when I'm going between different groups. So U is in one of my groups here, and the parent of U is in the next group. Because remember, the rank of the parent of U is more than the rank of U. So when I'm going from U to its parent, I might be traversing from, for example, a vertex of rank 3 to a vertex of rank 4. So I might be going from one group to the other group. So my second case is going between groups. Okay. And by the way, I'm assuming that the parent is not the root here because I've counted that in C1 already. And of course, I will also have a C3, which is the case where I'm going within the same group. So this means that both U and its parent were in the same group. Okay. Now I want to find bounds for each one of these numbers. So how many times does it happen that I go from U to its parent and the parent is already the root? That's the number of steps I'm taking in C1. This is actually the easiest one to compute, right? So if you look at C1, so I have n operations, right? In every operation, I'm reaching the root at most once, or well, exactly once. So C1 is basically equal to n, right? So I just say C1 is in ON. Because every time that I'm doing find root, there is only one time that I'm going from some vertex to its parent, and the parent happens to be root. Okay. How many times do I go between groups? Well, to answer that, I have to first ask you, how many groups do I have? So you see, the groups were based on ranks. And I know that the rank of a vertex is at most log n. We've proven that many times before. So the number of groups is going to be log star of log of n. But log star of log of n is basically log star of n. It's just -1, right? So the number of groups that I have is O log star n. Let me do it like this. The number of groups is O log star n. So this means that when I'm going between groups, I can do this at most log star n times in every operation, right? So every operation is a find root. I'm starting at some vertex u. I'm just going to the parents until I get to the root. So I'm starting somewhere, and I just keep going up, and maybe I'm in the same group, maybe I go to the group above, and so on, until I stop at some root. But I have log star n groups, so I can go between groups at most log star n times in every operation, and I have n operations. So this shows that my C2 is in O of n log star n. Great, I'm very happy with these two bounds for now. But now I have to prove the same thing for the last part, C3. If I can prove that C3 is also in O of n log star n, then their whole sum is also in O of n log star n. So how many times can I go from a vertex to its parent and remain in the same group? Okay, so I want C3. Now, in order to find C3, I'm going to first fix some vertex u. So consider any vertex u here. The question is, how many times do I go from this vertex u to its parent? And u and its parent happen to be in the same group. Okay. Now, here's the thing. If I look at the vertex u, I can just look at every other vertex that was a parent of u at any point in time, right? So originally, u didn't even have a parent, or u was its own parent. And then we did a bunch of link operations, merge operations, and the parent of u changes over and over. And mainly, the parent of u changes when I'm doing path compression, right? Because here, for example, let's say if this vertex was u, its parent used to be this one, but then after the path compression, it's directly going to the root, so the parent is the root. Okay, so here's what I'm going to do for this vertex u. I say consider the vertex u and consider all of its parents. So let's P1, P2 to PT, let's say, be its parents during all operation, during all operations, the whole process. So every time that the parent of u changes, I just remember what it is. Okay. What can I say about these parents? What can I say about the ranks of these parents? Well, the rank of P2 has to be bigger than the rank of P1, right? Because how did the parent of U change from P1 to P2? It changed in a path compression where P2 was the root and P1 was not the root, right? So that means that the rank of P2 was definitely bigger than the rank of P1. And then the same thing between P3 and P2 and so on. So if I look at the list of parents of U, they have increasing rank. Great. So I want to find C3. I want to find how often I'm going from a vertex to its parent and they're both in the same group. Well, I can just sum this up. I can say this is the sum over all of my groups. Let's say over all the groups that go from I to 2 to the power of I. Sorry for this notation. 2 to the power of I minus 1. Okay. And then I need another sum, the sum of all vertices U that are in this group. Okay. Times, well, here's the thing. I went from U to each one of these parents how many times? So the cases where these parents were the root was already covered in C1, right? So I'm only counting the number of times that I went from U to P1 and P1 was not the root. This can happen only once because then I find the new root and then I connect U directly to that new root, right? So for each one of these parents, I'm going from U to that parent at most once in C3. But how many of these parents can I have? Any ideas? I've lost my other notes. Okay, so all of my parents are supposed to be in this group. So they're supposed to have ranks that are between I and 2 to the power of I minus 1. But they also have different ranks. So the maximum number of parents that I can have is the number of different ranks between I and 2 to the power of I minus 1. So it's 2 to the power of I minus I. But let's just over approximate it. So instead of saying C3 is exactly this, I say C3 is at most this, and let's just put 2 to the power of I. Okay. So now I have this thing. I know that my total cost is going to be the sum over all the groups, and then the sum over all U's that were ever here times 2 to the power of I. Okay. Now, the number of groups is fine because I know that I have log star n groups. So if I can just look at this sum, and if I can say that this sum is in O of n for every one of my groups, then I get what I want, that the entire thing is in n log star n. But what is this sum? This is basically 2 to the power of I times the number of vertices that were of this particular rank, or that were ever in this particular group, sorry. So I have a range of ranks in this group. So what U's am I counting here? I'm counting all the U's that could possibly ever during the execution of my algorithm be in this group of ranks from I to 2 to the power of I minus 1, right? But here's the thing. This would be less than or equal to sum over all the groups that are from rank I to rank 2 to the power of I minus 1. Now, I have my 2 to the power of I times this U. If it were ever in this group, it means that at some point in the execution of my algorithm, it had rank I or I plus 1 or I plus 2 all the way to 2 to the power of I minus 1. Now, remember this lemma that we had here. Where is the lemma here? So this is the number of elements that had a rank of k at any time during the execution. So 2n over 2 to the power of k. So the number of elements that had a rank of I at any time during the execution is 2n over 2 to the power of I. Right? The number of elements that had a rank of I plus 1 at any time during the execution is at most 2n over 2 to the power of I plus 1. And so on. So I have to sum this up to 2n over 2 to the power of 2 to the power of I minus 1. Right? 2 to the power of 2 to the power of I minus 1. It's like this. Whatever. Okay. This is the sum that I have now. Let me move this. Okay. What is this sum? again, we constantly have sum of powers of 2. So it's like 2 to the power of I, and then the next one is 2 to the power of I plus 1, and so on. So every term is half of the previous term, right? So this term is half of this term, the next term is half of this one, and so on. But again, it's not going on forever. It's going to some weird place. But let's just assume that this is a series that goes for forever, and then just get a bound, right? So this would be less than or equal to the sum over all of my groups that go from I to 2 to the power of I minus 1, 2 to the power of I times. So this is at most twice the first element. So it's 4n over 2 to the power of I. Okay. Now, of course, the 2 to the power of i's cancel out, right? So this is the sum over all of my groups of 4n. How many groups do I have? Log star n groups. So this is just 4n log star n, which is in O of n log star n. Okay. So that's what I have, which means that my C3 is also in O of n log star n. So I have C1, which was in O of n. I have C2, which was in O of n log star n, and C3, which was also in O of n log star n. So their sum is in O of n log star n. So my total runtime is in O of n log star n, which means that the amortized runtime for one operation, for one find root operation, is O of log star n. Okay. I don't expect you to be able to do this in an exam. Don't worry about this. Okay. Now we have 20 more minutes. I want to show you another data structure. So remember when we talked about heaps, and we actually only talked about a very specific type of heap, which is called a binary heap, right? Basically, the idea here was that every vertex has 2 children. Like I have a complete binary tree, except for the last level, which might not be complete, and so on. But in a binary heap, what were some of the operations that we were doing? Let me see. I have the names here now. Okay, so let's say I had an operation called push, which basically adds 1 element to the heap. So push x. I had an operation called pop max, which removes the maximum element from the heap. I actually had an operation called max, which just gave me the maximum element. What else? Let's say I also had the operation increase key or increase priority, where I take some value and I increase it. So I had to bubble it up. Okay. Okay. Now, what was the worst case execution time for each of these operations in a binary heap? So if I wanted to push a new item, I would just add it to the end of my heap and I would bubble it up. But the height of my heap was at most log n. So this was O log n. If I wanted to remove the maximum element, the situation was very similar. We would just take the top element, the root of the heap, swap it with the last element, remove the last element, and then bubble down the root. And because it could go down by only log n steps, this was also O log n. Finding the maximum was super easy. This is O1. It's just whatever you have at the root. And increasing one of the keys, if I had a value in my heap and I wanted to increase it, I would just increase it and then bubble it up. So it's very similar to push. This is also O log n. Okay. Now, the problem with a normal heap is that even if I want to do amortized analysis, I don't really get better runtimes than the worst case execution time. Now, I want you to consider a situation where I'm doing a lot of push operations, but not a lot of the other operations. Okay. And I mean, this kind of situation actually happens in the Kruskal algorithm, for example. Right. So I want to have a different data structure where the amortized runtime of a push is much smaller. But I'm fine if the runtimes for the other ones remain the same. And this is where we get to what we call a binomial heap. Now, to define a binomial heap, I should first define a binomial tree. So a binomial tree is a very specific type of tree, and it's defined inductively. So I can define a binomial tree based on its degree. And when I say a binomial tree of degree k, I mean that the root of the tree is of degree k. So this is not a binary tree. A vertex can have many children, okay? So here's the thing. A binomial tree is like this. A binomial tree of degree 0 is just one vertex. So degree 0, this is a binomial tree of degree 0. If I want a binomial tree of degree 1, I have to take two binomial trees of degree 0 and make one of their roots the child of the other one. So it would just be 2 degree 0s, and then one is a child of the other. If I want a binomial tree of degree 2, I would just take two binomial trees of degree 1 and make the root of one of them a child of the other one. So it's just this. I take two copies, and one of the copies, the root becomes the child of the other copy. And so on. Generally, if I want a binomial tree of degree n, I would take two binomial trees of degree n minus 1 and make the root of one of them the child of the root of the other one. So degree 3, for example, would be this. It would just be two binomial trees of degree 2. And then one of them, the root becomes the child of the root of the other one. Okay? So this is what I have. What is the height of a binomial tree of degree k? It's just k, right? So the height of a binomial tree of degree 0 is 0. The height of this one is 1. The height of this one is 2. It's easy to prove by induction that the height is the same as the degree. But how many vertices do they have? So a binomial tree of degree k would have 2 to the power of k vertices. That's also very easy to see just by definition, because I have two binomial trees of degree k minus 1, and I'm merging them together, so I get twice as many vertices. Okay. Now, what is a binomial heap? A binomial heap is just a bunch of binomial trees. So a binomial heap is a set of binomial trees. Now, the really important point here is that all of the trees in this set should have different degrees. I would not allow you to have two trees of. Okay, so a binomial heap is a set of binomial trees of different or distinct degrees. And of course, I'm talking about a heap. So I want to say that I have a key or a value or some number at every one of the vertices. And I want to say that they satisfy the heap property. So every vertex has a value that is greater than or equal to all of its children. Okay. Each vertex satisfies the max heap property. That's it. That's my data structure. Very simple. Of course, not as simple as a binary heap, but at least good enough. So let me take some of these, let's say, and copy them. Let me give you just an example of binomial heap here. So maybe I have this binomial heap. And oh, by the way, I don't have to have all the possible degrees. So maybe I have a tree of degree 1, I don't have a tree of degree 2, and then I have a tree of degree 3. So the only rule is that I cannot have two different trees of the same degree. Okay. And at every vertex, I have some value. So maybe here I have, I don't know, 10. Here I have 6. Again, it should satisfy the heap property. So 11, 2, 5, 7, 4, 1, minus 1, minus 5. Okay. These are the This is how my data structure looks like. And now I want to do these operations. So first of all, max is kind of hard now. If I want my maximum element, I have a problem here. Because I have all these roots, and I know that my maximum element would be at one of the roots, but I don't know which one. So if I want to find my max, I have to go over the roots of all of my trees and take the maximum. But that's too hard. So instead, I'm going to just change my data structure a little bit and say that I also have a pointer to the maximum element. I know this sounds like cheating, but I can keep this pointer. Okay, so my data structure is a bunch of trees plus a pointer to the maximum element. So now, if I'm doing this in a binomial heap, and let's say that I'm looking at amortized runtime, I can still say that my max is taking O1, and I'm happy with this because it's the same thing that I had for my binary heap. I just want to make my push faster. Okay. How would you do increase key? So let's say that I want to increase this key. For example, it was -5 before. I want to increase it to 8. Well, this is just like a normal heap. Just increase it and then compare it with its parent. If the value is bigger than the parent, bubble up and keep doing that. And of course, we just proved that the height of our trees is going to be at most log n, right? Because a tree with height k has 2 to the power of k vertices. So this is going to take O log n as well. So increase key, O log n. Pop max. If I want to remove the max, how do I remove the max element? Well, this is a little bit trickier, so let me come back to it later. Let's do push. Push is easier. Let's say I want to push. So I want to push some element here. For example, I want to push, let's say, 8. What I do is very simple. I just create a new tree of degree 0, and I put this new element there. Okay, so I just create a tree of degree 0, and 8 is there. That's how I push. Now, let's say I push again. Let's say I now push, whatever, now this time, let's say 12. Okay, again, I create a tree of degree 0, and I put 12 here. But now I'm violating the rule that I cannot have 2 trees of the same degree. But as soon as this happens, I can merge them into 1 tree of the higher degree. So I have 2 trees of degree 0, the 8 and the 12. I just merge them. And merging means that I take one of the other root, right? Which one should become the child? Of course, the one that has the smaller key. So 8 has to become a child of 12. So I would just put 8 here, and it's a child of 12. But now I'm still violating the rule because I have 2 different trees of degree 1. So I would just keep merging. So now I have 10 and 12. 10 should become a child of 12. So I'll just merge them like this. Now I finally have a valid heap because I have 1 tree of degree 2 and 1 tree of degree 3. That's fine. Okay, so that's my push. How much time does push take? Now, to answer this, we have to first ask, how many different trees can I have? Look, all of my trees have different degrees, and a tree of degree I has 2 to the power of I nodes in it. So I can have at most log n different trees. Okay, so I have at most log n different trees. When I'm doing push, I'm adding 1 element, I'm adding 1 new tree of degree 0. And then I might have to merge it with another tree of degree 0 that I already had. And that gives me a tree of degree 1. Then I might have to merge that with a previous tree of degree 1. And I might have to continue this. So the worst case runtime is actually O log n, because I might have to do 1 tree merge for every possible degree of trees. Okay. But we will come back to the amortized runtime. What about pop max? Now, if I want to remove the maximum element, for example, here, actually, I don't want this to be the maximum element, so let's say this is 10. And actually, let's say this is 9. So I want to do pop max in this situation. I want to remove the maximum element. Remember, I have a pointer to my maximum element. It's 11. Okay. Now, here's how I remove it. I know that it's a root. I just remove it. So I'll remove it. And now, the problem again is that I have to do some merging, possibly. Because now I have 2 trees of degree 2. I might have to merge those two. So this one has 10 at its root. This one has 7. So 7 becomes a child of 10. So I have to put this here. And then 7 becomes a child of 10. Okay. But I can do the same argument as before to show you that pop max also takes O log n. Because pop max basically creates a bunch of new trees. But it creates at most 1 tree of degree 0, 1 tree of degree 1, 1 tree of degree 2, and so on. And then I first merge all my trees of degree 0. Maybe they give me a tree of degree 1. Then I merge my trees of degree 1. Maybe they give me a tree of degree 2. And I keep doing that. Okay? So this is also taking a worst case runtime of O log n. But now it seems that we are just where we were before. Like all of our runtimes, all of our worst case runtimes are the same as a binary heap. So why do a binomial heap at all? Because we can actually get a much better result here if we look at amortized runtimes. Here's what I want you to consider. Each one of my trees has a number of nodes that is a power of 2, right? And additionally, all of them together have n nodes. So what is my n here? For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my n here is 11. Actually, the number of elements that I have uniquely determines the structure of my heap. Why is this? Because I basically have to write 11 as a sum of powers of 2. And there's only one way to do that. That's the binary representation of 11. Right? So the binary representation of 11 is that 11 is basically 8 plus 2 plus 1, right? So 11 in binary is 8. I don't have a 4. I have a 2. I have a 1, right? So now if I look at these digits, so this is the 0th digit, 1st digit, 2nd digit, 3rd digit. This tells me that I have to have a tree of degree 0. I have to have a tree of degree 1. I don't have a tree of degree 2. I have a tree of degree 3. Okay, so the binary representation of my number n is giving me the exact format or the exact structure of my heap. It tells me exactly which trees appear in my heap. Now, what happens when you're pushing a new item? When you're pushing a new item, you're basically increasing this number by 1. So this is just like the increment operation that we saw, right? So you're adding 1, which means that, well, I'm adding 1 here. And yes, it might be that I have to do a lot of merges. But the amortized runtime is actually O1. Because every time that I'm adding this, again, I can just look at the last digit, same argument as the counter. The last digit changes every time that I do push. The second digit changes every 2 times. The next digit changes every 4 times, and so on. And every change corresponds to 1 merge that I'm doing in my trees. And every merge was done in constant time. So my amortized runtime is the same as the amortized runtime that I had for my counter. And at the very beginning of this session, when we weren't yet out of time, I showed you that the amortized runtime of increment on a counter is just O1. And again, for pop max, we saw that even our worst case runtime is O log n, so I can give it an amortized runtime of O log n as well. And as you see here, all of my runtimes are the same as before, but now I have an amortized runtime of only O1 for push, which means that if I have some sort of a use case for my heap, in which I do a lot of pushes. The number of pushes that I do is much more than the number of pop max and increase key operations. Then this is a much better data structure, because my total runtime here would be number of pushes times 1 plus number of pop max times log n plus number of max operations times 1 plus number of increase key operations times log. So this is a better heap. And actually, we're going to see another heap which is even better than this one. It's called the Fibonacci heap. And that one is going to use, well, actually, I can just give you a video to watch on that.